Hi, Jim. Let me know if you could unmute yourself as well once you get on. I don't see that you have a microphone yet.
Peter or Tommy?
Yes. Hi, Jim.
Yes, hi, Jim.
Oh, I just want to be sure you're there, Tommy. I'm here just to check in with you. I've got all the background information, so just let me know when you want me to proceed.
Okay. Yeah, I'll let you know. You got a little bit of a background echo, but it should be okay.
Okay. Well, I'll mute only when I have to speak.
Okay.
Hopefully it'll be okay.
Sounds better now. Okay. Thanks.
Okay. Thanks.
Okay, hello everyone. I want to welcome you all to today's continuing NEARI LEHIGH seminar series. I wanted to note that if there are any technical issues, please contact us through the chat and we can look through that. And please wait to the end of the presentation to submit any questions or raise your hand or use the chat window or just unmute yourself, and then we could have a candid discussion about the topic at hand. This time I'd like to introduce Dr. Jim Rickles to please welcome our speaker.
Yes, hi everyone. This is Jim Rickles. I'm the director of the NEARI LEHIGH Experimental Facility. I want to welcome everyone to the seminar. This is one of several seminars that we hold within our series, and today we have Dr. Yelda Turkan from Oregon State University, where she's the assistant professor of construction engineering and management within the School of Civil and Construction Engineering. Her doctoral degree is from the University of Waterloo in Canada. She has a lot of research interests and experience, particularly in the areas of remote sensing, computer vision, and machine learning applications for construction engineering and management, in addition to infrastructure, asset management, and transportation. Want to note that she's the vice president of IARC, which is the International Association for Automation and Robotics for Construction. And she also serves as the chair of the ASCE Computing Division Education Committee. So with that, I want to welcome Dr. Turkan, and I'll hand the podium over to you, Yelda.
Oh, hi. Thanks.
Yeah, hi, Yelda. Yeah, thank you.
I was muted.
Okay, that's okay. Thank you.
All right. I just need to share my screen. Can you see my screen now?
Yes, we're good.
Okay, great. Thank you for the introduction. Yes, I'm an assistant professor in the School of Civil and Construction Engineering at Oregon State, and my background is more in geomatics engineering, and today I'm going to talk about these technologies, LiDAR, drones, and BIM technologies. And then I will talk about a couple of research projects we have done using these technologies, and how we can talk about how we can leverage them for post-event reconnaissance.
I just want to know quick, before you continue, your presentation went into like the split screen mode. I don't know if you could fix that.
Is it good now?
I mean, you could do that. That's fine. We were just seeing your, your layout and all. So if you want to do it this way, it's up to you.
Yes, sorry, Yelda. Right now it has the non-presentation mode. Sorry, I didn't mean to interrupt, Tony. Sorry. So on the left side, it has all your slide footprints, and now it's split screen. So whatever you prefer to use, I think that one's better than the prior one. Whatever you prefer.
The prior one. Okay, sorry about that.
All you would have to do is, if you went into, sorry to interrupt, to go into the slideshow mode, you change your display settings to be your primary monitor to get rid of the side-by-side.
New share.
So if you do, sorry, if you just start your slideshow.
Okay, let me see here.
Correct.
All right. And then new share, or
right, you see at top of your display settings, we could get rid of the next slide in the notes.
Did it work now?
No, it's okay. All right, we'll go back to, instead of wasting everybody's wasting time, we could go back to just doing it the previous way, side by side.
Okay. Sorry about that. All right, I'll just go back to this. Is it okay now?
Yeah, that should be fine. You could continue.
Okay, all right. Sorry about that. So for those who may not be familiar, I wanted to first talk about these technologies. When we say LiDAR, many I'm aware of that the steer gear communities are now collecting LiDAR data. For those who are not familiar with it, LiDAR stands for light detection and ranging. What you collect using LiDAR, also referred to as laser scanning, 3D laser scanning, you collect three-dimensional point clouds. Each point in that data set has XYZ coordinates and RGB values associated with each point. We have, based on the platform that is used, we can categorize LiDAR into three categories. There's the aerial, mobile, and ground-based LiDAR. You can tell from the name is that the aerial LiDAR is typically a LiDAR unit is mounted to an airplane. That's the least accurate LiDAR type. The accuracy you get is 0.2 to 1 meter. Typically used by DOTs. They collect the data for the entire state and they use it for planning purposes, not for construction or damage evaluation or anything like that. Mobile LiDAR, as you can see here, the LiDAR unit is typically mounted on the back of a truck. It is much more accurate compared to aerial LiDAR. Again, it is used by DOTs and by construction companies as well for collecting as-built data. The accuracy is much higher, millimeter to centimeter. One thing about mobile LiDAR is that this can be, it could be very practical to use it after, let's say, an earthquake. When you go to that site, it is very practical. However, it is there may be a lot of noise in the data that needs to be processed first. And the ground-based LiDAR is the one that you mount on top of a tripod. It is the most accurate. You can get up to sub-millimeter accuracy. And based on the technology, we can also divide the LiDAR into two categories: time of flight and phase-based. For the physics, from the physics perspective, the time of flight sends the laser pulse, receives it back, and measures the time for it that it takes and calculates the XYZ coordinates based on that. And phase-based basically looks at the phase differences between the two laser pulses. So the phase-based ones are typically have shorter ranges. So they're better for indoor applications. If you're collecting data from an inside of a building, it is better to use that one. And time of flight laser scanners are better suited for long range applications. You can collect data up to 1 kilometer typically. LiDAR is not a new technology. It has been around since 1970s. However, it was expensive. The accuracy of the equipment that was available was not very good. Within the past 10 years or so, there has been an exponential growth in the LiDAR market. A lot of, especially in the architectural engineering and construction industry, there has been companies are investing now into laser scanning and laser scanners and use it for a variety of purposes, such as scan to BIM for construction quality analysis, progress tracking, and simply documenting as-built status of their projects. How it works, I briefly already talked about this. The laser pulse is emitted, it hits the surface, and then we get the data from the surface. So lasers, they're in the near infrared portion of the electromagnetic spectrum, so it collects data from what it sees. It's not going to see the backside of these targets. So if we wanted to get a 3D dimension of these targets, we will need to collect multiple scans and register them in the same coordinate system, so that we have a complete three-dimensional image of our target. Another thing is that the further from your target is the sparse your points, you'll get sparse point cloud. So if we're aiming to get data from this building facade here, the points we will get, they will be sparse. So if depending on our application, if we want to get a quantify or measure damage, we want to get closer to our target. Again, a couple of application areas we can, if we want to get the as-built data for a project, we can get multiple scans and combine them together in the same coordinate system. Here, for example, we took scans from 38 different points, indoors and outdoors, and combined them all together in the same coordinate system. We did this and then we compared it to its S-plan building information model. It has been used a lot, LiDAR equipment has been used a lot for scan to BIM applications. A lot of older buildings, they don't have three-dimensional planned S-plan building information models. So when they want to renovate these buildings or power plants, they go ahead and collect laser scan data, and there's commercially available software enable us to fit pipes, walls, those type of three-dimensional objects into our point cloud. We can also use it for damage assessment. So far, majority of the efforts is to use LiDAR point clouds for manual assessments. We can, the point cloud software that is available enable us to manually measure the damage and use it for further purposes. It has also been as I mentioned at the beginning, the LiDAR point clouds, many steer gear groups collected LiDAR point clouds. This is a data set my colleague Dr. Olson collected from the earthquake, after the earthquake in Nepal in 2015. Again, this is a combination of multiple laser scans of a temple in Kathmandu. Here in this system, there's a 3D virtual reality system here in the geomatics lab at OSU. We can, with the tracking cameras, a user can experience can have an immersive experience with the data. Let's say if it's a structural engineer, can go and look into the temple and look at the damage that is in there. Some of the data, this is not exactly earthquake data. We use LiDAR data for floor flatness analysis. This is a thing in construction engineering for quality control. After they pour the concrete, this is especially important for warehouses where they need to, because in warehouses you have forklifts, they're stacking materials, so the flatness of the floor is very, very important. And once they pour concrete, traditionally they use surveying equipment, straight edges, F-number methods. So it takes them a long time to do the floor flatness analysis. In this research project, what we did was we used LiDAR data, we collected LiDAR data, and then we converted our three-dimensional LiDAR data into a two-dimensional depth map and applied continuous wavelet transform to our depth map to detect and localize the undulations on our surface. So we use the terrestrial laser scanner to collect the data, like a P40. Another thing to mention is that on this LiDAR equipment, we also have a high-resolution camera on it. So that once you finish collecting the laser scan, you can also collect images and then overlay those images on the laser scan point cloud, so you have a more realistic looking laser scans. For this project, we collected 4 laser scans, 4 scan point clouds, and each scan took about 9 minutes to collect. So what we did, this is our registered point clouds, and this shows the depth map. You can see the differences, elevation differences on the surface here. And then but we wanted to, here you can visualize it. We wanted to be able to find those differences on the surface automatically. So we applied the continuous wavelet transform, and as you see here, we were able to see the differences automatically. This can be very important, let's say after an earthquake, let's say this is a hospital or a warehouse. It would affect the hospital equipment, the way it works. It may not function as well, right? So the flatness of the floor is important, and we can leverage LiDAR data to be able to automatically tell. Moving on, drones are becoming more and more popular. They're cheaper compared to laser scanner, and we can mount different types of sensors on them. We can put regular digital cameras or thermal cameras, and we can also attach drone to these to the unmanned aerial system. So obviously there's their capacity. We cannot really put LiDAR mount LiDAR equipment that is very heavy. So in terms of that, is a little limited. We actually use this for one of our projects, and we were able to collect sparse LiDAR data, and we are still working on the comparisons between. We wanted to use it for floor flatness analysis. We are comparing the results of that with the terrestrial laser scan data, because the terrestrial laser scan data is much more dense compared to the drone LiDAR data. So for the images, there is the structure. If we can collect images using drones, and we can convert those images into 3-dimensional point clouds. So there is a commonly used method. It's a structure from motion. It basically combines the basic principles of photogrammetry and computer vision. So it looks into so the drones come with software, and you need to plan when you're collecting your images. You need to do a flight planning, and those images have to have 80 to 90% coverage among them. So those coverage is used. The common points between those images are used for feature detection. That is, the principles of photogrammetry as well as the computer vision are used together, and then the camera positions are recorded, and using that, the 3-dimensional point clouds, dense 3-dimensional point clouds are built from that. The software, the commercial software packages that comes with that, they're highly automated and fairly easy to use. Here you can see this is a point cloud, 3D point cloud you can obtain from from drone images. Again, this is another example. You can create a 3-dimensional point cloud from those images. This is an example of a bridge, and then I just wanted to show the resolution. You can go and look into your image. So again, by comparison, what the 3D point cloud you would obtain from a drone can be dense, but compared to what you can get from a LiDAR, it will not be as dense, and the point cloud you get from a LiDAR will be more accurate. So we used BIM, in one of our previous projects, we combined building information models and UAS imaging for bridge inspections. So what we did was we developed a three-dimensional model of a bridge, and then we used the images that we collected from using a drone, and then we were able to detect those defects on the concrete bridge, and we were able to integrate those, map those defects onto our 3D model using the industrial foundation classes. It's a natural file format is used for BIM. And then we were able to integrate those in the data cloud so that it is accessible in the field as well. I will talk more about that. So this was our image processing overview of our, I guess, image processing. So we determined this is a bridge in Eugene, Oregon, and it was classified as structurally deficient. So we wanted to collect data. We first got the 2D plans from the DOT, we converted them into a 3D model. And then we took our drone, we collected images. First we did flight planning. We decided on our control points. And we did an image acquisition. So we first flew our drone to collect overall images, and then we, looking at those images, we from the parts that we saw cracks, we sent our drone again and we collected more high resolution images. And then we applied image processing. We applied several image filters and the bottleneck transformation, and then threshold segmentation. We were able to label those cracks automatically. Here you can also see these are images that we collected using the drone. You can see them visually, but our goal was to find them, identify them, and label them automatically, and which we did here. And then once we identified those cracks, this is our three-dimensional bridge model in the IFC. This is not something we did automatically. It can be done automatically. We were able to alter these 3D objects and enter the information related to the damages. So here, there's a hairline shrinkage crack. So we were able to enter that information. And then this is a BIM model. Once it is integrated, this BIM model can be put in the cloud and can be accessed from an iPad or Android tablet computer in the field. And then once you click the object, you can see if it is damaged and what type of damage. Also, the images can be associated with that particular object. This project, we also shared this with bridge inspectors in the DOTs, and they thought it would be very useful. It is not fully automated, but this can be also something useful for when you're collecting data from earthquake sites. And then the other project we worked on is using LiDAR data for detecting those cracks. So LiDAR data, one of the biggest problems with LiDAR data is it can be very, very large. One single LiDAR point cloud can be in the gigabytes range. So the processing can be very challenging. In this project, we collected laser scans of concrete specimens that were cracked in laboratory conditions. Then we used adaptive wavelet neural networks to identify those cracks automatically. what adaptive wavelet neural network does is that it fits a surface, so we were able to represent our surface using several nodes instead of using hundreds of points to represent that crack. So it basically improves it basically cuts down the processing time of the point cloud, of the LiDAR point cloud. So we are working toward expanding this work and applying, our plan is to apply to an entire building and see, look at the computational time. This is somewhat still future work. We are looking into using deep learning algorithms. We're planning to apply those algorithms to LiDAR point cloud databases and train our algorithm that way, and then compare our results with the as-built BIMs, and then come up with or generate as-damaged BIM models, and then we can then compare our as-damaged BIM models to the as-built BIM models. How we can do this? This is an example of it is from the earthquake in Turkey in 1999 in Izmit. So, and this is a point cloud of the exterior only, right? If a building this might damage this much, you don't want to go inside. One thing that can be done, if we have the 2D drawings or the 3D as-built model for this building, we can then come up with several scenarios and look at the as-damage run structural analysis algorithms and look at the as-damage version for this building, and then from then we can compare with the LiDAR point cloud. And then this is another example from the 1999 earthquake in Turkey. Again, the image of the building, and then this is the LiDAR point cloud and the BIM model. So we want to be able to go from the LiDAR point cloud to BIM and map those damages on the BIM model. So then we can use the BIM model for further structural analysis and for remodeling, repairing those buildings. And this is all I had. Any questions? I think I saw several questions here.
Thank you. Do you want to go through the chat and read? There's a lot of data going on, a lot of conversation going on there that could be, looked through on your own to see if you want to, how you want to reply.
Okay. Sure. All right. All right. Now I see the there are some computational time. So the Yanlin asked how much computational time does it take to build a 3D point cloud photorealistic model using LiDAR? So it really depends on the accuracy you want, or the density depends on the density of the point cloud and your target object. That example I showed you from the warehouse, each laser scan took us about 9 minutes. And this is the laser scan we obtained. We didn't use the highest resolution. So if you want the highest resolution, it may depending on the size of the object you're scanning, that may be a couple of hours or less. It really depends. And then the photorealistic model is the, most of the laser scanners now come with built-in cameras. So it takes extra time. So you can do the laser scan first, and then it takes, depending on the laser scanner you have, the Leica P40 we have, it takes another 10-20 minutes, depending on the object we are scanning, to take the pictures, and then it overlays those pictures on the point cloud. And Brett is asking the, I'm guessing it depends on the software, automated, okay. Excuse me. The as-built model equate the as-built information. So the BIM model is the as-built information that we created from the 2D as-built drawings. And the results may be affected if you're not using the accurate as-built model, I believe. I have not used drones for post-earthquake damage analysis yet. We can again collect the images and apply similar methods to images, or we can develop point clouds from the drone images to evaluate the structural damage. BIM model can go into structural analysis software. So there are different Revit enables exporting in different formats. This could be a DWG, RVT, and majority of the structural analysis software accepts you can import into the structural analysis software as a BIM model that would enable the enable for structural analysis.
Okay, if anybody wants to open up discussion, speak, you can unmute yourself or raise your hand. We'll give just another minute or two to see if anybody wants to have any other conversation. Okay, Jim, if you want to give some closing remarks, I think we're going to conclude at this point. There are no other questions coming through.
Okay, I think there was one question that's interesting, Yale, it's near the bottom from Yang Lin. It said, do you convert BIM model to structural model for analysis? In other words, the relationship between the information you collect in the field or you have in a database, and that you want to use for structural modeling to assess the response and integrity of the structure.
Right. So we can develop a structural model for. Obviously, we need the structural drawings, but to develop that, and I guess, does this mean from LiDAR to structural model for analysis? Convert BIM model to structural. So it depends on the data you have, but it can be converted into a structural model for further analysis.
Mm-hmm. Okay.
And
Yella, there's another question. Sorry, I didn't mean to interrupt. Go ahead.
I just saw another question at the bottom here. How do you measure deformation in point clouds? Is it based on change detection? Yes, but we also, as I mentioned in the previous work, we used wavelet neural networks to measure those deformations, such as cracks.
Hmm. On those measurements of deformation, can you reduce the field so that you don't have to have as much data, but you can get rapid measurements, so you can try to monitor, say, the motion of a few points rather than a bigger window? Is that possible, Yale? I guess it's a matter of arranging the field of view and the scans and everything, right?
Exactly. Yeah, we can clean the point cloud, and then we can only look into the area of our interest. And then here in this case, I don't know if you can see my screen, but when I was talking about the structural condition assessment, where we use the adaptive wavelet neural network, there we were only interested in that area. So.
Can you measure velocity, or is it slow? What is the rate you think of the displacement or velocity you could measure? So I'm thinking if someone wanted to do system identification to either ambient or forced vibration of, say, structures in the field, and as you may know, sometimes it's hard to instrument structures because you may not have access to them and may be unsafe, but yet you always have ambient vibration. Do you think you can use the technology to try to measure motion? You can try to get, say, modal characterization data. You know, it's going to depend probably on the rate of which you can
measure
the data.
Measure the displacement of the volume in the structure.
Well, to give you an example, let's say you just visualize a flagpole and you have 4 points over the height of that flagpole, and you like to try to identify the motion of that structure when it's subjected to, say, someone impacting the ground nearby. Would you be able to track that motion as it vibrates, say, due to the loading, or not that many points, just selected points? It doesn't have to be more or less a continuum. It could be very discrete.
Yeah, I guess it could be done when collected.
Okay.
Yeah, if you collect it frequently, before and after.
Okay, thanks.
I think you could do that with accelerometers that are, put in the building.
No, the point is that you don't have access to the structure. So you can always use lasers, I guess, but you don't have access, so you can't place anything on the structure. It's either forbidden or it's unsafe to get near the structure.
So then you would have to have the LiDAR running continuously to catch the event?
No, I think you have to have it running where you can collect the data. Yes, you have to have the LiDAR running during the event that you're going to create.
I guess, yeah, that would be. I mean, I would collect the data before and after. I don't think collecting the data continuously would help. Maybe using a video would be, videogrammetry could be a better solution to that.
Okay, yeah, thanks. Sorry, I didn't mean to interrupt. Are there any other questions? I know, Yelder, there's a number of, in the group chat, I guess the chat is evolving here. I don't know if there's anything there we may have missed, or if anyone else has any questions maybe that they did place and we missed, that you can just speak up on the microphone if you want to ask the speaker any other questions there at this point.
Sure. Are there any questions? I guess I see one question by Brett asking, I thought BIM were created before construction and using construction. That's my confusion is with post-construction as built. Typically, contractors, they update their BIM model as they go during the construction phase. So as built BIM model is delivered now, the owners are asking for it. So the as built, back in the day it was as built drawings. Now they deliver as built BIM to the owner.
Oh, okay, great. That makes sense.
Okay, are there any other questions from anyone? Well, yeah, it sounds like there's no other questions. I think what I was going to suggest, if anything comes up or someone has a question, I think your contact information, your email address, they can always get it probably just online. Just go to your department. There it is right there. So it's easy enough. They could follow up with any email. That's what I'd recommend at this point if they have any other questions. And, I wanted to thank you for offering to give this seminar. I thought it was very interesting. I think it was gives a very good overview, and it seems like there's a lot of potential, and it's an evolving field here of all the new technology that's evolving. So with that, again, I wanted to thank you, and I'm sure the audience feels the same way. They're very appreciative.
Thank you for the opportunity, Jim. Thanks everyone for joining us today.
Great. Thank you.
And again,
Sorry, are you okay with us archiving this presentation on the Design Safe website?
Sure.
Yeah, we'll do the video, the actual recording of it, not the actual file. So if anybody wants to come look at it, it'll be archived there.
Okay.
Great. Thank you.
Okay. Thank you again, Yalda. So again, anyone has any questions, please feel free to email the speaker there. And with that, we'll go ahead and close the seminar today.
Thank you.
Okay, thank you. That'll conclude our seminar.